While Uwe is setting up, let me tell the story of this, what's happening now. This is about a building kit for neural networks. Neural networks is the big thing we've gotten so many questions about for the last kind of 2 years, about how to teach them in Snap, how to show them in Snap. At one point, Yadka was at a conference in Berlin of teachers sitting together, deciding on which tool to use to teach neural networks. And they were threatening to use a tool that is also a block-based language that we thought should not get it. So Yadka just explained, no, we can do this in Snap. We'll have this ready in a couple of months. Jens is already working on this. And she texted me, oh, Jens, I've just claimed that we know how to do neural networks in Snap. And I said, oh, good, great. We're just gonna, we're just gonna build it in and, do it. And then we started working on neural networks. And at first, we were really making good progress. Like I was able to understand the first 5 pages of Nielsen's book, and then it was all Greek. And I knew why I studied law instead of mathematics. And so it trailed along really for months and months. And we didn't get any farther. And then we decided to ask people who knew about this. And one people who knows about stuff is Uwe, who's a math teacher. Math teachers know everything. And we had a bunch of sessions with Uwe. Every couple of weeks, we met at SAP or somewhere here in downtown Heidelberg, Yadka, Uwe, and me, and we decided on ways how we wanted to teach it, but we couldn't kind of really figure out how to actually code it up. Luckily, neither could Uwe. Together, we sort of found enough clues to guide us through this, and Uwe is going to tell you kind of the first part of the story, and the second part I'm going to show you later. Okay, Uwe, take it away.
Yeah, hello, and welcome to the talk. I warmly welcome you all, and I'm happy that so many people are interested in our building kit for artificial neural networks. So my name is Uwe Lorenz, so maybe I will skip the detailed self-instruction because there's so much to say about that and so little time. And so genau, I will be sharing today's presentation or the topic with Jens. In my part, I will make a few introductory remarks on the basic principles and ideas of machine learning with artificial neural networks. And Jens will then introduce how you can discover and acquire these principles and ideas in a creative way with Snap environment for yourself. And so I'm a little proud that I was able to use my math teacher skills not to help Jens with the theory behind this algorithm, but he found a wonderful way to implement this in Snap. And so you found a way, so maybe this presentation is a bit the preparation for the hot stuff. Jens will present later, probably in the, doesn't work anymore? Yeah, maybe in the final keynote this evening then, you will see. So first, yeah, I would like to start with a small classification problem. It's about selecting objects, in this case bottles, with specific properties. And the task is to select specific bottles from a high number of these, and maybe this one that can hold 2 liters of a liquid. And the problem is a bit simplified. There are exactly 4 different types of bottles here. Very large and wide and small ones. And so, this naturally raises the question, isn't there a machine for that? Can we not automate that? And yeah, I played a little bit around. Maybe you know this problem. The Snap really makes you want to tinker. And oops, where is it? Here is it. it's maybe you have these bottles, and it's now there are sensors, and then they get some properties, and if they fit to the desired features, then they are selected or not. So maybe the link is in the slide. So maybe you want to play around with that. I like that very much. And so yeah. So we have here this more general, maybe this classificator. Maybe so I have to start here with this presentation. So but the problem is the question, how to code this element, the classifier here, and there are two very different types of approaches to solve things like that. There is a classical approach, a rule called rule-based approach, so where the information processing is programmed, and a developer has to enter a program that describes how the input is processed. So I have to think about rules that help to decide, or that I can use to decide whether an object belongs to my desired class or not. So it's, everyone knows how this looks like. And yeah, but there's also the possibility to do this different in another approach where the information processing is trained. And here we have it's a little bit different, and there are two different phases here, because we have a training phase where we enter training examples, and then we also enter a learning algorithm, for example, a neural network with backpropagation. And then we have optimization loop where we have incremental improvements, and the system has to figure out how it can recognize in the patterns what response is required here. And after the training phase, we have the deployment phase. So if the model is sufficient, useful, then we use it. And maybe so how does it work? And maybe this work. The perceptron, many of you probably heard of this. It's a minimal artificial neural network, and even so, as we will see, the capabilities of these systems are limited. It's good for illustrating central concepts and ideas of machine learning with neural networks. And you can think of it as a kind of elementary computational element that contains maybe some strange type of code, the model parameters, and an interpreter that converts this into an output. And with reference to artificial neural network, to natural neural networks, to biological models, this interpreter is also called an activation function, and is implemented in the perceptron in a way that the weighted sum of the input values is fed into the activation function, and which then triggers an output when the sum exceeds a certain threshold value. And so very simple model, but you can do a lot of stuff with it. And so yeah, I have a bit cybernetic FIML, so that's why I always say it. So I like these feedback loops, and the idea is, how does a perceptron learn? And the idea is start with an arbitrary poor state and gradually improve the model. And and we have here a loss. It's a difference between a target and output value, and then the learner where the loss is multiplied with the input values. In fact. And L is just the parameter for the learning rate, something like a step size, something like that. And yeah, so, and how does it would look like in our framework? Jens will present, and it's kind of we have some blocks that we can build such a perceptron here in an easy way. Maybe I have to look at the time. It's how much time is it again?
More than 5 minutes.
We can realize these things very easily here, and Jens will present these later. And yeah, so and if we want to change something. In type A approach, we have to think about the rules again. So we have now, or if we want to have bottles that hold at least 1 liters, and in type B solution, we have to make a change to the training examples. Maybe it's partially true, but because we changed the desired target. I think this little difference is, for me, it's very important because we change the direction of the optimization process, and I think this is important for understanding the power and the risk because of the autonomy of these systems when adapting and finding relevant features on their own. And task three picks the bottles that hold exactly 1 liters. So we got the problem because our perceptron cannot do this. Maybe if you know some theory behind it, that there's no line that we can separate these classes. And yeah, we have to improve the model and the topology. And yeah, in our there are blocks for that. So Jens will present. Oops. Genau, da ist noch ein Audiosignal drin. But we can be optimistic because all these elements of an XOR are possible to implement in a perceptron. We saw it's just OR and AND. And so we can combine this, and we've get a multi-layer perceptron. So it's just plug these multiple perceptrons into, 3 perceptrons into each other, and we get a kind of additional hidden layer. And yeah, we're doing supervised learning, old school, kind of behavioristic. So the question is how to adapt this complex thing here. And there are 2 steps. We are replacing the threshold value with a continuous function. So we don't have this anymore, but a more continuous one. That is can be gradually changed. And then another algorithm that's a bit more complicated, but Jens found a very nice way to solve this. Yeah, we have also a forward pass where activations flow through the net. And then here the activations are stored because we need this later for the backward thing. And oops. Let's make too much automat here. And we will see that now it calculates the loss. And yeah, we get the loss, and then we get a kind of error that is also similar to the delta rule, is used to change these weights here. And then the question is how to propagate this backwards. And here we have kind of that we use these. Maybe the crucial question is that is difficult. What part did a single node here play for the error in the following layers? And the idea for the backward pass is take the weighted error, like here, and multiply it with the net input activation that came in the forward pass. So we have here kind of 2 things coming together, the forward and the backward, and this was not so easy to implement. But here, so this is, I think, the basic idea, to bring this together, the weighted error here and the activation of the forward pass. But Jens will show you how to understand this more concrete, more hands-on, more creative. And so maybe this is kind of preparation for the hot stuff. Jens will show us this later. So thank you.
Thank you. So Uwe showed us where all the problems are, and then helped us solve them. And now he's sort of in this position that he showed us the problems, and he was going to show you the solution.